Okay, hi everyone. This is going to be our second video on 7.5, which is on surface integrals of scalar functions. So we're just going to do another example here quick. The double integral over s of 1 minus z ds, where s is the graph of z equals 1 minus x squared minus y squared with x squared plus z squared less than or equal to 1. So again, this 1 minus z is going to be our f of x, y, z. And in order to compute the surface integral, we're actually going to first have to come up with a parameterization of s, and then we're going to use the formula which was shown last time, the double integral over d of f of phi of uv, where this phi of uv is our actual parameterization of the surface S, multiplied by the size of the normal vector t of u cross tv. And these tu and tv, of course, are the tangent vectors in the u and v direction. And then we integrate that du dv, right, over d. Okay, so the first thing we're actually going to want to do here is come up with parameterization of the surface S. So I already have the graph here. So this z equals 1 minus x squared minus y squared. This is a paraboloid, which you can figure out by testing a few z level sets of the equation. And then we have this extra condition that x squared plus y squared is less than or equal to 1. So z, which is 1 minus, in parentheses, x squared plus y squared. If x squared plus y squared is less than or equal to 1, when we subtract it, we get something that is greater than or equal to 1. So 1 minus 1, which is, of course, 0. So z is greater than or equal to 0. That's what this x squared plus y squared less than or equal to 1 condition gives us. And, of course, just the graph of the paraboloid, 1 minus x squared minus y squared, that has the condition that z is less than or equal to 1. Since x squared and y squared are both going to be positive numbers, or certainly less than or equal to 1, be equal to 1 when x and y are both 0. So that's how you kind of get a grasp on the graph on the actual surface S before coming up with this parameterization. So the first step now is we actually want to come up with parameterization for z is 1 minus x squared minus y squared. And so your instinct here might be that to let just x and y be our parameters. And then since we already have an equation, z equals 1 minus x squared minus y squared, that you already have it. You know, you could do, of course, like x equals u, y equals v, and then z, you already have the equation in terms of x and y. So 1 minus u squared minus v squared. And that'll work. But so, of course, feel free to work it out using this parameterization on your own, and then see if you get the same thing that we get at the end. We're actually going to use a different parameterization here just to kind of get some practice with parameterization. So also, we know from the book that these surface integrals are independent of parameterization. So if I use one parameterization and you use a different one, you should still get the same answer. So what we're actually going to do here is begin by rewriting it. X squared plus y squared is 1 minus z. And now we're going to kind of think of this like a circle of radius square root 1 minus z. So then it becomes, well, if I'm thinking of this like a circle, then I want x and y to be cosine and sine theta times the radius. So cosine theta and y is sine theta. Of course, I left this blank here because we need to multiply by the radius of the circle. And now the radius of the circle actually depends on z. And so this is a circle centered at 0, 0 with radius square root of 1 minus z. So what we're going to do is we're going to let z equal our other parameter. So maybe we call it r. R because it's what determines the radius of the circle. And now the radius is square root of 1 minus r. So y is square root 1 minus r sine, and x is square root 1 minus r cosine. So this is the parameterization we're actually going to use here. Like I said, you can use the x equals u, y equals u, z equals 1 minus u squared minus v squared parameterization, and you should get the same answer. But we're going to use this. So phi of r theta is square root 1 minus r cosine theta, square root 1 minus r sine theta, r. So then f of phi of r theta, all right, we need this and for the equation, right? We have the equation is, we need this f of phi of u v. Now here, u and v we've replaced with r and theta, but nothing wrong with that. So we need to find out this, which is, well, f we already established this is 1 minus c. So, well, z is r now. So f of phi is just 1 minus r. Okay. So now we need to find our tangent vectors in order to find the normal vector. So tr, differentiating with respect to r now. So square root of 1 minus r is like the 1 minus r to the 1/2. So we get a 1/2 and a negative from the chain rule because 1 minus r is on the inside. So negative at the 1/2 puts 2 on the bottom. And then we're left with 1 minus r to the negative 1/2. So square root 1 minus r is now in the denominator. And then the cosine theta is just a constant multiple. So it hangs out on top. Same thing is going to happen over here. Square root of 1 minus r, again, is what we're taking the derivative of. So we get negative divided by 2 square root 1 minus r, and then the sine theta just stays. And of course, the derivative of r with respect to r is 1. Now t theta. This one's a little easier. So cosine theta we know goes to minus sine theta. And sine theta goes to cosine theta. And r goes to 0. Now let's compute the cross product. Tr cross t theta. Right, because our end goal, we need to actually find the size of this vector. So first let's find the vector. We do sine theta over 2 square root 1 minus r times 0. Well, that's 0 minus the, so 0 minus the square root 1 minus r cosine theta. Okay, and then we get square root 1 minus r sine theta times 0. Okay, so this is, negative 1 minus r sine theta. And then finally, computing this last one here. So when you're multiplying like this, cosine time, right, the first component of TR times second component of T theta minus here. Okay, so in each of these factors, the square root 1 minus r cancels out, right? You have one in the numerator, one in the denominator. And then in the first multiplication, you get cosine squared negative cosine squared over 2. And then when you compute the second one, so you have minus, now the negative times the negative cancels out. So you have minus, again, the square roots cancel, and we have sine squared over 2. Okay, so if you factor out the negative here, square root 1 minus r cosine theta, square root 1 minus r sine theta, and here you have cosine squared plus sine squared all over 2, which is just 1/2, because cosine squared plus sine squared is, of course, 1. Okay, now let's compute the size of this normal vector. Of course, the negative doesn't matter on the outside there. So we square each one of these and we add them together. Well, you get 1 minus r, because we're taking the square root squared, cosine squared, plus again 1 minus r sine squared. Okay, so you can already smell that. We're going to be able to simplify here. 1/2 squared is 1/4. So we can factor out the 1 minus r and get cosine squared plus sine squared, which again is 1. So 1 minus r plus 1/4. So our norm here is 1 plus 1/4 gives us 5/4. Square root of 5/4 minus r. Okay. So now we need to figure out the bounds of integration. So what do we have? We have r and we have theta. So we actually want theta to map out the entire circle. Again, we want these full circles to draw the graph of the paraboloid. So theta, of course, is going to range from 0 to 2 pi. And for r, well, r is just z. Okay, so z goes from 0 to 1. Right, so z, oh yeah, sorry, r. We're calling it r, but it's z, so this ranges from sorry, it's from 0 to the graph of the paraboloid, right? So from 0 to 1 minus x squared minus y squared. Well, this is set up so that x squared plus y squared is actually just 1 minus r. Right, so this is which is just r. Okay, so now this may be a little confusing. So what we get from this is really the bounds. The bounds for z are just constant. So the z values we're actually looking at are from 0 to 1. Okay. So the integral, last step here, just setting up the integral. Theta goes from 0 to 2 pi. Z goes from 0 to 1. Our r goes from 0 to 1. Our function is 1 minus r. And the size of our normal vector was the square root of 5/4 minus r. So this is the integral we want to compute. And so what's good here is that our integrand is constant with respect to theta. So this outer integral, the integral d theta from 0 to 2 pi, we can deal with that just by multiplying by the length, right? 0 to 2 pi has length 2 pi. So this is just 2 pi times the integral from 0 to 1 of 1 minus r square root 5/4 minus r. Maybe you remember how to deal with integrals like this, maybe you don't. But a simple way to deal with this, I think, is to make the substitution. U is 5/4 minus r, which says r is 5/4 minus u. We're going to need that. But also that du is just minus dr. So this integral is 2 pi. When r is 0, we get 5/4. And when r is 1, u is 5/4 minus 1, which is 1/4. And now we get 1 minus, well, r, okay, is 5/4 minus u, so negative of a minus u is plus u. And now we just have square root u here, so this is why it's helpful to make this substitution. So this is 2 pi. We can get a negative, right? We're going from 5/4 to 1/4, which is the opposite of like what intuitively we would go from. So we can switch the bounds here if we multiply by a -1. So instead of having u minus 1/4 on the inside here, we get 1/4 minus u. Okay, and then on the outside is just u to the 1/2. Okay, so now you're seeing, well, this is just the integral 1/4 to 5/4 of 1/4 u to the 1/2 minus u to the 3/2. And now all you have to do to compute this integral is use the power rule for integration. And I'm not going to get into the nitty gritty of this. Of course, everybody knows how to do this by now. But if you work this out on your own, so you should get something like 2.97 And that's it for this video. So we'll move forward into 7.6 next time.